Location of minimas. The mathematical procedure to determine the location of maximas is beyond the scope of this course because it involves solving complicated integrals called Fraunhofer diffraction integrals. However, there is an alternative technique using phasors. These are complex vectors in the complex plane to compute these locations of maximas. Phasors are considerably easier to compute than the Fraunhofer diffraction integrals, but under our current circumstances, I'm not going to do it because the maximas are so much more complicated to try to understand. The minimas are not. So I'm going to focus on calculating the locations of the minimas. Without the mathematical rigor required to understand these locations, in summary, the locations of maximas is approximate for the first three secondary maximas. The fourth secondary maxima and beyond can be determined quite accurately. Minimas, on the other hand, have their locations exactly determined to all orders. The angular locations of minimas is determined exactly via the path difference equation, where the path difference is an integral number of wavelengths. Unfortunately, these path differences are not derived as those of interference for two slits. But without the mathematical structure of phasors, I will only state without proof the condition for destructive interference. That is, if I have a path difference of a sine theta, then I'll have destructive interference when I get an integral number of waves where ND is equal to 1, 2, 3, etc. And this path difference is that of wavelets, not of waves. This is what you get for single slit diffraction minimas. Let's make some remarks on this relationship. 1. The only parameter about the whole opening is the A parameter. The key signature of diffraction is the A parameter and must not be confused with the D parameter of interference. In summary, if you see the A parameter, then one is talking about diffraction. If you see the D parameter, you are speaking about interference. 2. Since there are equal number of minimas on either side of the central max, the number of minimas depends on whether ND is an integer or is not an integer. So let's do the first case, which is ND is an integer. If ND is an integer, then the number of minimas is equal to 2 times ND. So if ND is an integer, so if it's 1, that means there's only one minima. Nothing exists beyond that. And 2, I have 2 minimas. And 3, I have 3 minimas. So therefore, the total number of minimas is then going to be 2ND, 2 times 1. So I get 2 minimas for both sides. In this case, I have 4 minimas. In this case, I have 6 minimas. But what about the number of maximas? So note that if I have 2 minimas, I only have one central max. And if I look at ND equals to 2, note that I got the center, and then I got 2 on both sides, so I got 3. So if I look at ND equal to 1, and I ask what is the number of maximas, you could see that I only have one peak here, and it's 1 less than the minimas. So the number of maximas is 1. What about for ND equals to 2? So I got the central, and then I have 2 secondary, so that's a total of 3 maximas. If I look at ND equals to 3, note that I got my central plus 2 here, so I got 2 here, 2 there, plus 1, that's 5. So look at the pattern now. If I have 2 minimas, I have 1 max. If I have 4 minimas, I have 3 maxes. If I have 6 minimas, I have 5 maxes. Therefore, I can write this in summary. The number of maximas is equal to 2ND minus 1. Applying these to these 3 cases here, so if I have ND equal to 1, then I'm going to get 2 times 1 minus 1, which gives me 1 max. If I have ND equal to 2, I get 2 times 2 minus 1, gives me 3 maxes. And then following, I get 5 maxes. Case 2, non-integer ND values. The easiest of these values are integers divided by 2, like 1.5, 2.5, 3.5, etc. What do these pictures mean? So if I look at ND equal to 1.5, then I know if I have ND 1 and 2, 1.5 is going to be in between these two here, so it's closer to a maxima. Remember, maximas, we only know their approximate locations for the first three secondary maximas. If I have ND equal to 3.5, then that means it's somewhere between the third minima and the fourth minima. So if I draw this out, when I get to the third and fourth, 3.5 then implies that it's closer to the third maxima. Now, what happens if ND is equal to 1.2 versus, let's say, 1.8? What does that look picture-wise? Now, if I draw the intensity pattern for ND equal to 2, I then get this picture right here. But what am I actually seeing here? What you're seeing here is that if I look at 1.2, we know that this here is roughly 1.5. So 1.2 is going to be roughly right there. 1.8 is going to be roughly right there. So in each of these cases, ND equal to 1.2, you're going to see a tiny bit of the maxima. And if you look at 1.8, you're going to see past the maxima, and you're going to see a dimming of this last piece of this bright spot. So let's draw the pattern. So if I expand on this pattern here, if I had ND equal to 1.2, what that means here is that I get the central max, and then I'm just going to get a little bit of intensity past N equal to 1. Whereas on 1.8 here, I have the central max, and then I see the peak, and then I start to see the dimming of the light, but I don't get all the way down to 0. So these fractional ND values tells you that you're getting partial light at that spot. Let's go use the diffraction applet from Fendt to predict the number of minimas and maximas. Let's go use the diffraction applet from Fendt to predict the number of minimas and maximas. I will break this down with three situations. The slit width is integer values of the wavelength. The slit width is half integer values of the wavelength. And finally, it being non-integers of the wavelength. So in this situation, the wavelength and the slit width are exactly the same. And if you look at the number of minimas here, you're getting, looks like you have one on each of the ends, where the only maxima is in the middle. Now, if I want to take that slit width and I want to make it twice the wavelength, I'm going to come in here and I want to type in twice the value, and I get this pattern. And you're seeing that I have two minimas on either side of the central max. And if I come in here and I triple this value to 3 times the wavelength, you're seeing here that I'm getting 1, 2, 3, 1, 2, 3, and let's go look at this numerically. On the Fendt applet, the first case is that we have a slit width where I have integer values of the wavelength. The two questions that I want to ask is, how many minimas are there? What angles are these minimas located at? And the three cases that I looked at is A equal to lambda, A equal to 2 lambda, A equal to 3 lambda. If that's lambda, then that's 2 lambda and that's 3 lambda. So how many minimas are there? In the first case, I have A equal to lambda. I know that the path difference equation is given by this relationship. Within the denominator here, I have the diffraction parameter. So now if I plug in my values, plug in ND equal to 1, you could see that I've already maximized it, but when I go to ND equal to 2, this has now exceeded it, and so this makes it impossible. So that tells me here is that there's only one minima on each side of the central max. Again, the sequent tells me that ND is equal to 1, which means I have one minima on each side of the central max. Let's go to a equal to 2 lambda. So in this case, at a equal to 2 lambda, my diffraction parameter, a over lambda, is 2. So that's how I got this 2 right here. Now I start the sequence. I get 1/2, I get 2 over 2, then I get 3 over 2. Therefore, I now have ended my sequence, implying that MD is equal to 2, which means I got 2 minimas on each side. So when I go and I look at the image, you could see here that I have one minima there, and then I have another minima right at the very end at 90 degrees. For a equals to 3 lambda, I got ND divided by 3, the diffraction parameter. I get 3 before the sequence truncates, so therefore I have 3 minimas on each side. So if I look at this guy right here, you could see that I got 1, 2, 3. If I look at the picture here, I got 1, 2, 3. At what angles are these minimas located? For a equal to lambda, we know that ND is equal to 1, so therefore the sine of theta 1, that is the location of the first minima, has to equal 1. That implies theta 1 is equal to plus or minus 90 degrees. Going back to the apt, you could see here for a equal to lambda that this location and this location is the minima at 90 degrees. If I now look at a equal to 2 lambda, we know that ND is equal to 2, so there are 2 minimas. So if I go back and I look at the sine function, you see that sine of theta n is going to be 0.5 or 1. So this tells me then, the location of the first minima is when sine of theta 1 is equal to 0.5, and the second minima at theta 2 should be 90 degrees. Computing these two angles, then theta 1 should be plus or minus 30 degrees, and theta 2 should be plus or minus 90 degrees. If we go back to the Fendt applet, you could see that the two minimas, ND equal to 1 is at 30 and minus 30, and ND2 will be at 90 degrees and minus 90 degrees, which is exactly what we calculated. If I now show you a equals to 3 lambda, that means ND is equal to 3, so there should be 3 minimas. So then the sine function that we computed up here is then going to have a value of 1/3, 2/3, and 1. If I now solve this for the angles that I'm going to get here is plus or minus 19.3 for the first one, the second one is 42.1, and then the third one is plus or minus 90. So now I have the a equal to 3 lambda situation, and let's go look at the minima. So his first minima is 19.5. Note that I calculated 19.3, but that's because I truncated 1/3 to 0.33. But if you were to add more sig figs, you would get 19.5. So the first one's at 19.5. The second one is at 41.8. And then the third one here is at 90 degrees. Exactly what we predicted. Case 2, slit width equal to half integer values of the wavelength. So if I have a wavelength of 570 nanometers, then the slit width in this case is equal to 2.5 times the wavelength. And what you're finding here is that I'm having, just by counting these, I'm getting 1, 2 minimas on each side. But we would think here, because of that 2.5 value that we talked about before, that should be a maxima. Well, for the first few maximas, we know that the maximas do not lie smack in the middle between two minimas. And you can see here that if I click on the very last one for the maxima here, you're seeing that the peak is not at 90 degrees, but close to 90 degrees. So what we want to do here is that we want to draw this picture as well as calculate the number of minimas and try to estimate where we are on the graph. So these are the locations of the minimas. So let's go back in and look at that for 2.5 lambda. And that means that this situation here is that I'm going to change this wavelength so that it's 1995. And what you're seeing here is that I get, for 3.5 times the wavelength, I get 1, 2, 3 minimas. Note that these minimas are not equally spaced. They shouldn't be, because it's proportional to sine of theta. So if I look at the minimas, you could see that I'm going to have 3 minimas, and these are the angles which we'll calculate. And then let's go look at the maxima now. The maxima at the end is still at 90 degrees, even though it's smack in the middle between, two minimas. This is the image from that applet, and again I have A equals to 2.5 lambda, A equals to 3.5 lambda. So what I want to do here is that let's go and predict these, minimas and also the angles. First thing I'm going to do is I'm going to look for the value of ND. This time I'm going to do it slightly different. Start with the path difference equation, and then I want the maximum value of ND. This value occurs when sine of theta is equal to 1. The max value of ND in this case is equal to 2.5. This means that there are 2 minimas, but not 3. So if I draw that picture out, it means that I have, looking at just half of it, I have ND equal to 1, 2, and 3. So we know it's between 2 and 3 here. Anything between 2 minimas, we always assume that it's going to be smack in the middle where a maximum is going to occur. But because we don't know how to calculate the locations of the maximas, this is roughly where that maxima is. To draw it to 2.5, I drew it in green here to show you that there's this little extra piece. That's what that 0.5 value means. So if I now look at the applet results, you could see here that at the end I'm getting what looks to be some type of secondary maxima right at the end right there. I want the angular locations of the minimas. I again go to that path difference equation where I get ND divided by the diffraction parameter, which is ND by 2.5. Following the sequence of MD here, I get 1, 2, and 3 exceeds it, so I only have 2 values, which we already knew. So sine of theta is equal to 0.4 and 0.8. Calculating these two angles for 1 and 2, I get 23.6 and 53.1. And if you come up here to the result of the applet here, I'm getting, as you see, 23.6 and 53.1. Repeating this for a diffraction parameter of equal to 3.5, if I want the maximum value of MD, I'm going to get 3.5. It tells me that there are 3 minimas for this pattern. I look at the intensity plot, I can see here that 3.5 is between 3 and 4 of the minimas here. So it's smack in the middle, but again, we don't know really if this is smack in the middle for maximas because the equations are nonlinear. Get these angles of these minimas, I then follow the sequence. Sine of theta is then going to be 1, 2, 3. When I get to 4th, you can see that I've exceeded sine of theta greater than 1, so now these are the locations of the 3 minimas. Computing these 3 angles, we see that we get 16.6, 34.9, and 59.0. Now if I go and I compare these to the applet, you could see that I'm getting the values exactly that's predicted. So that ends that for now. Last case is with the slit width equal to a non-integer values of the wavelength. So I'm going to pick these 2 quantities. I have A equal to 1200 nanometer, where the wavelength in each case is the same, and then the other aperture size is going to be 1550 nanometers. So when I calculate the diffraction pattern, I get 2.11 and 2.72. Basically, what does this mean? Since the maximum ND value is equal to the diffraction parameter, for the first case I get 2.11, the second case I get 2.72. I look at that 0.11 value, what does that mean? Well, 0.11 means it's just past the second minima. As in this case, the 0.72 means it's approximately just past the maxima. If I plot the first one, that 2 tells me I have 2 minimas, but there's a little tiny bit of maxima right there. That's that 0.11. If I plot the second one, I got my 2 minimas, but note I now have 2.72, so if this is 2.5, this whole little bit right here, or this little tiny bit, is really 0.22 past 2.5, and so you're just past the maxima, approximately. Go put these values into the applet. So in our first prediction for 1200 and with wavelength 570, what you're seeing here is that the pattern shows that I see a minima here, a minima there, but note that there's a little bit of the edge here. So if I go and look for the maxima, they give a maxima at the 0 degrees, and they give a maxima at 42 degrees right here. But note, that is not a maxima, or else the arrow would tell me that that's a maxima. So that means here that this is more likely a very, very dim, and it's just past the minima. So this agrees with our picture. Here's our second case that we looked at. Again, we're seeing 2 minimas as expected, but I really want to look at this maxima here. So if I look at the maxima, there's the first one, the central max. If I go, here's the secondary. Now look at where the second one is. The second one is right there. But note, the maxima is here, so that means I'm coming down the peak right here. And if I'm coming down the peak, this is where I'm getting that 0.72. So this picture is agreeing with what we just saw.